Hi everyone, this video is all about binary search. So let's start with some basics. So binary search is useful for searching elements in some sorted array. We all know that. It is a kind of a divide and conquer algorithm and blah blah blah. Oh wait, are we missing something here? Yes, the time complexity. The time complexity of this algorithm is log of n for array of length n. What exactly binary search means? Let us understand. Binary means 0 and 1. So we can say that binary search is equivalent to 0-1 search. So let's see some example. Suppose we have bunch of zeros and one in some sorted manner. So what kind of problems we can solve using binary search? We can either find out the last zero in the array or we can find out the first one in that array. Let us solve a problem using binary search. So the problem is find the position of first one in the following array. So we have an array of zeros and one in sorted manner. We have to find out the position of the first one in this following array. So initially our search space itself is whole array. So our left index is 0 and right index is 14. And what we do, we find out the middle element which is at the position array of 7 and the value is 1. So we can ignore the elements to the right of it because we already got 1 at our middle position. So either this is our first one or the first one lies in the left of it, but it can't be in the right of it. So now our left index becomes 0 and our right index becomes 7. So what we do now, we again reiterate this. So if our left index is 0 and right index is 7 now, what we do, we find out the middle of these. So the middle of these is 0 plus 7 over 2, which is equal to 3, and the array of 3 is 0. So now we can ignore the elements to the left of the middle and the middle itself, since our first one lies on the right to it only. We have now our left index at 4 and our right index at 7. So see, our search space has been decreased dramatically after we do these operations. So let us reiterate. Now left index is 4 and our right index is 7. So let us find out the middle of these. So middle of this is 5 and array of 5 is equal to 1. So again we have found 1. So we can ignore the elements to the right of it because we already got 1. So either this is our first one or the first one lies to the left of it, but it can't be in the right half. So if we see now, our left index is 4 and our right index is 5. And we can see only very few elements are remaining in our search space. So let's reiterate. Now left index is 4 and right index is 5. So we need to find out the middle of these. So 4 plus 5 by 2 will be, as integer division is 4 and array of 4 is 0. Now since it is 0, we can ignore elements to the left of it and the middle element itself, since our first one lies on the right to it. So now what we will do, we will increase our left index by 1. Now what happens here, we will be left with the left index as 5 and right index as 5, and we got only one element. So now we found the answer at the 5. Till now, we played with zeros and ones only in the name of binary search. Now let's play with other numbers as well. So here we see another problem. Find first element greater than or equal to 18 in the following array. Clearly it is 19 here. So let's apply some trick and transform this array into some known one. So yes, we will replace each element with 0 if element is less than 18 and with 1 if element is greater than or equal to 18. So now you can see this array has been transformed into the array which we previously saw, and the answer for this is finding the first one, which we already did with the binary search. So binary search can be applied here as well in this sorted array. Now let's move on to something else. This is the code for binary search written in Python. This is the simplistic binary search which is being taught in the college program. So if you see, this helps us in returning the exact element in the sorted array. Now let's see the animation for the previous code. Now if you see, we have this array from 0 to 16 indices and we have to find x is equal to 1 in this array using that code. So I'll start the animation. You can pause or you can think through this animation to find out how this works. Now let's compare the two binary searches we just saw. So here is the example. This is the example of simplistic binary search where we need to find out the exact element. So here we have to find out the 4 in the following array. Now let's look at some other example. So this is more competitive programming related example. So you need to find out the first value greater than or equal to some element. So this is commonly used in competitive programming, and you can compare both of these two codes for the binary search, and you will find out there is the difference in the while condition and in if and else conditions. Let me know guys if you want me to make videos on these comparisons as well. Okay guys, now I want you to focus on one more important thing. Sorted array can be visualized as monotonic non-decreasing function. What does that mean? So from any sorted array we can create such kind of graph. So here x-axis represents the indices of array and y-axis represents the value in the sorted array. And the yellow dot is the searchable value which we want to search using binary search. So obviously the exact graph for an array will be a discrete one, but just for sake of simplicity we have taken a continuous graph. That means any sorted array can be visualized as monotonic non-decreasing function. Now let's dig deep into the graphs. Suppose we have a representation of a sorted array as monotonically increasing function. So here if you see left index and the right index are the endpoints of the graph, which are also endpoints of our sorted array, and the pink dot here is the searchable value in that array. Now suppose we are in the orange portion of this graph. That means all the values in the orange portion are greater than that of the dots value, which is the searchable value here. So we might need to decrease our right index to approach the dots value. Similarly, if we are in the blue portion of the graph, we might need to increase our left index value so that we can approach the dot, since all the values in the blue portion are lesser than that of the dot. Now similarly, we will take example of monotonically decreasing function. Here we have orange part and blue part, and the yellow dot is a searchable value here. Now suppose we are in the blue portion of the graph. That means all the values are lesser than that of the dot value. That means we will need to decrease our right index to approach the searchable value, which is the dot here. Similarly, if we are in the orange portion of this graph, we will need to increase our left index since all the values in the orange portion are greater than that of the dot value. Now let's take some example with the combination of both. Here we have increasing decreasing function where we have only one maximum value. Now in the orange portion and in the blue portion as well, both the values are lesser than that of the dot value, which is a searchable value. So we don't know either we will need to increase our left index or we will need to decrease our right index. So how do we solve that? Yeah, there is a trick for that. So if we are in the left portion of the graph, what we can do, we can choose two consecutive point, one main point and one left point. Here, if we are in the left portion of the graph, our left point will always be lesser than that of the right point. So we will know that we will need to increase our left index to approach the dot value. Similarly, if we are in the right portion of the graph, we know that our left point will always be greater than that of the main point. So we will need to decrease our right index in this portion of the graph to approach the value of the dot. Here you can see that we have solved the increasing decreasing function as well using binary search, where we can always find the maximum value in the graph using the binary search. Main point here is to note that we have only one maximum. We do not have multiple maxima here. Now let's take a look to other graphs as well. So we have already seen that monotonic increasing graphs we can solve using binary search when we want to find out some value in this graph. Similarly, we can use binary search in monotonic decreasing functions as well. Now we can have single maximum or minimum curve as well, where we have only single maximum or minimum value. We can apply binary search over there as well. Now this graph. So this is a sinusoidal graph where we have multiple maxima and minima. So here we won't know like in which portion of the graph we are. So we cannot directly apply binary search over these kind of graphs. We have seen a few examples how to solve graphs using binary search. Now let's take a look at some other example. So here on the x-axis we have the indices of the array, and in the y-axis we have the values in the array. So my question is, find the position of third number from 7 in this array. Can we find it in log of n time? What do you think, guys? So let's try to think and come up with some solution, guys, and try to post that answer in the comments below. Now let's move on and take a look at the main part of this video, which you guys might be looking for: identifying binary search problem on the following online judges: codeforces, codechef, hackerrank, hackerearth, Spoj, or anyone. By using these methods you can actually identify the binary search in any of these. Let's start, guys, how to identify binary search problem on following online judges. I will list down few of the rules which you can apply to find out if a problem is a binary search problem or not on these online judges. So let's start. On the first thing, if you know the possible set of answers, then you can apply binary search. So for applying binary search, you need to know what are the possible set of your answers, obviously. And the second rule is you can create similar graphs of search space, which we have already seen. We have seen few of the graphs, right? So if you can create one of those graphs, then you can apply binary search as well. Other thing is interactive problems. You see many interactive problems on the codeforces. On those kind of problems also you can easily apply binary search. And the other thing is finding the maximum and minimum value on the curve. So if you have a curve and you need to find out the maximum or minimum value, then you can apply binary search to find out that. The other thing is, if your problem can be reduced to a 0-1 problem, then also you can apply binary search. That means some of your answers will result in 0 and some of your answers will return in 1 based on some condition. Now the last point here is maximize the minimum value and the vice versa. So you may find out these phrases in your problem statement that like maximize the minimum values or minimize the maximum values. Using these set of rules, you can actually identify if your binary search problem is there or not. So I think it will work 99% of the time, and you should be able to identify almost 99% of binary search problem using these set of rules. Also, guys, let me know if you want me to create videos on each of these rules separately and discuss these in details. Now guys, let's see some competitive programming problem. This problem goes as follows. There are n stacks of boxes. All boxes have same dimensions as one unit. The height of stack is defined as the number of boxes in it. So if you see, we have 3 stacks here of height 3, 1 and 2. The initial height of ith stack is given as hi. We need to equalize the heights of stacks by adding, removing or moving the boxes across the stacks. The cost of each of these operations is defined as following. The first thing is, if we add a box on top of a stack, it costs us a. So in the example, if you see, we have 2 boxes and we add some other box on the top of it, it costs us a. The second thing is, if you remove a box from top of a non-empty stack, that costs us r. So we have 3 boxes in this stack, we remove the top one, it will cost us r. Now the third operation here is moving a box from top of a non-empty stack to top of another stack costs us m. So if we move a box from top of a one stack to another stack, it will cost us m. What we have to do, we have to minimize the cost in such a way that all the heights of all the stacks become equal. Here are the constraints. n should be less than or equal to 10 to the power 5, a or m should be less than or equal to 10 to the power 4, and height should be less than or equal to 10 to the power 9. I want you guys to solve this out. I will create another video to discuss the solution for this problem. Till then, you can try your best to find out the most optimal solution for it. It is a kind of a division 1 C problem. You guys can post the solution for this problem at my email address. I will post my email address in the description of this video. That's all folks for binary search. And yeah, there is more to come. Be it dynamic programming solving, recursion states, segment trees, Fenwick trees, or binary search tree, lowest common ancestor, Prim's algorithm. There's too much. So please comment down below on what topic do you want next video on. Also, we can include other topics as well, like design patterns, low level designs, high level designs, system design, and other stuff related to software engineering. Last but not the least, a big thanks to all of you guys for watching this video. I hope you learned something new. Any kind of feedback will be appreciated. If you don't understand some parts of this video, feel free to ping me or rewatch that part. You can connect with me on following media handles. These will be posted in video description as well. Also guys, it takes hours to come up with such videos. So if you guys can support me over Patreon or buy me a coffee, that will be highly appreciated by me. And that will propel me to make new videos with awesome quality content. Also guys, I apologize for any sort of technical glitches in this video, be it audio quality or anything else. We will try to improve on. Thanks guys again for watching this video. Bye bye and happy coding.